In this video, we're just going to remind you of some fundamental principles and how we approach differential equations and modeling in general. An important goal as you work through the different models, as we see different applications, is not to memorize the differential equations and their solutions. These techniques are widely used in a variety of areas, and the important skill is to be able to translate the relationships that you see in a given field into mathematical equations, which are often differential equations. But it's that translation skill that's fundamental to doing that, and that means understanding the actual area itself, recognizing which effects are insignificant and which are important, and we're going to explore a bit looking at special cases and specifically equilibrium solutions in a variety of topics. The idea is to focus on those themes rather than getting lost in the details of a particular model and trying to memorize the details of that one instance, because that's probably not going to spread across or generalize to other applications. As a starting point for a discussion of more general models or more complicated models, we're going to focus on the models of growth and decay, and specifically exponential growth and decay. The principle behind those is always the same, that the rate of growth or decay is proportional to the amount present. And that is a perfect translation of those words into mathematical formulation. dp/dt is a rate. The equals of k times is the proportionality. And proportional to what? Well, to the current amount. So translating that sentence into mathematics naturally leads to an equation with a derivative in it, and this interesting relationship where the derivative depends on the value of the unknown variable, here p. Once we have that insight into how a system might work, then it takes some work, but it takes some processing, but we can either guess and check, or we can use the separation of variables to get to a solution. Notice this has no derivatives in it anymore, and it has a form that we might not expect just looking at the equation until we have a little more experience. It has this exponential form to it, and how do we know that this is correct? We can sub into the differential equation, and we will find that the left-hand side is equal to the right-hand side. Taking a quick look here, what is our p? It's an exponential e to the kt times k, that's our right-hand side. And what would the derivative of this expression be? It'll be the same expression, but with the chain rule, a k is going to pop out, and so we're going to end up with k times what we started with. That would be the left-hand side. So we're going to get the same thing on both sides, and that's our definition of a solution to any equation. If we have k larger than 0 in that exponent, or in this term here, it's actually easier to understand from the differential equation side. If this multiplier is positive, then what we're saying is that the rate is positive and that we have exponential growth. Because the derivative is positive, the function is increasing. And that's if we graphed p against t. And if we had a k less than 0, then we'd have some population or some radioactive quantity multiplied by a negative number to give us the rate. We'd have a decreasing function that would translate to a negative exponential in our solution. What we're now going to do is explore other ways we can form differential equations, looking at modeling examples, and then how to construct and interpret their solutions.